let me get started here. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day, and I thank you for these students in this class. Just pray that you'd guide our steps, help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, first order of business, the end of last class, the proof I gave at the very end of class had a flaw in it, right? I ended up with something like b times 1 minus jk or something like that, equal to 0, right? And I was like, well, what if b is equal to 0? But what was the context of that proof? A and b were what at the end of last class? Remember? They were natural numbers. Is 0 a natural number? No. So did I need to argue that b was non-zero? I did not. It was already apparent. Like, I didn't need that argument there. All right? Now, there's a different version of that example we did at the end of last class where you could say, A and B, so I'm not going to do this one today, but I'll just tell you. If A and B are integers, all right, and A divides B and B divides A, then A is equal to plus or minus B, all right? That is true, and essentially you could get that more or less twisting the argument I gave last time just ever so slightly. But anyway, so there's that. So let me start with our next proof for today. How about this? Let's start out with example 1. So here's the claim. Given A, B, C are integers, if A divides B and, if A divides B, then, my bad, A divides BC. So that's my first claim for today. We'll start out with that. So hopefully today we'll do a bunch of proofs. So I want to illustrate to you different methods of proof, right? This is what we're doing right now is a direct proof, right? Essentially, what do I have? I have the logical structure here is a conditional. You could think of this as what? So this is like P, right? This is like Q. And basically, we're trying to show that P implies Q. Like that's the general structure that we're after here, right? So a P implies Q proof, a direct proof, what you do is you begin by assuming P is true, right? So here's the proof. Let A, B, C be integers, and suppose that A divides B. All right? Then there exists M in the integers such that B is equal to M times A. Right? If A divides B, that means B has to be a multiple of A, which is to say it's M times A. This is the definition, which I hope you wrote down. All right, so then what? Thus, BC, oh man, sorry, I just got just a second here. Yeah, so what's BC? BC is equal to what? So we can take the B and replace it with what? MA times C. But by properties of arithmetic, we can rewrite that as what? This is MC times A, right? Where MC is an element of what? M is an integer, C is an integer, so M times C is again? An integer. And what does this show? Thus, A divides BC, by definition, of divisibility. I can't spell maybe I spelled divisibility. It's anybody's guess. I tried to spell divisibility. My apologies for the spelling mistakes. They could be worse. Believe it or not. So that's a direct proof. We assume the antecedent and we show that the conclusion necessarily follows. That's it. Let's look at another one, unless there's a question. Example 2. If A and B are natural numbers, and A divides B, then A is less than or equal to B. All right, so let's work this out. So proof looks like this. We assume A and B are natural numbers, and A divides B, right? Then there exists, let's say, K in the integers, right? Such that what? B is equal to K times A. Notice, what can we say about K? So we know how to, we know arithmetic, right? So now some instructors might not allow you this step, but I will allow you this step provided that you don't, anyway, I'm going to allow you this step. I hope it doesn't backfire on me. So anyway, so we can do, so why can we do this? Is defined since A is not equal to 0, right? So I figured that out since last class. Natural numbers are not 0. That matters now, right? Can't form a fraction unless we know the denominator is non-zero. Hopefully that was part of your quiz answer. Right, rational numbers are the set of fractions such that the denominator is not 0, and the fraction is formed by a quotient of integers. Okay, so, great. Thus, what? As A and B are greater than or equal to 1, we find K is greater than 0, right? Agree? So K is greater than 0, but K is an integer, right? Thus, K is actually greater than or equal to 1, right? So really, we could say that K is a natural number, as it happens. Now, I defined divisibility in terms of integers, right? But if you look at this, we could also define divisibility just in terms of natural numbers if we wanted to, but I didn't do that. So we have to go through this. Right? Because we don't know before the fact that this multiple K, we don't know that this is positive without establishing that, right? But now we have. K is positive, right? Then, if we look at B is equal to, what was it? Ka is greater than or equal to what? 1 times A, right? So I have, if you don't like this, we could do it a different way, but K is greater than or equal to 1. So I'm taking K and I'm replacing it with 1. So this, of course, is equal to A, which is to say what? B is greater than or equal to A, also known as AKA A less than or equal to B, and we're done. All right. Now you might say, well, this is obvious, right? I mean, come on. If A divides B, that means B is a multiple of A. Of course, B has to be larger than A, or equal to it, right? That's true, but now we proved it, right? Example 3. This one's a little different. Oh, wait a minute. Oh, yeah, I can't do this one yet. All right, so at this point, I have to address a kind of, well, I don't know what to call it, a sticky wicket. It's a kind of a surprisingly difficult thing. It's obvious, but yet the proof of it, given our current technology, is not easy, I would say. And this is the simple observation. Given an integer, right, then either x is even or x is odd. How would you prove this? All right. So in your homework, I ask you to prove that if you have, I basically ask you to prove it's impossible to have an integer that's both even and odd. That's a homework problem for you guys. That one's pretty easy. You can prove that by contradiction. You just assume that it's both even and odd. Put those two together, you'll get 0 equals to 1 pretty quick. That's going to be one of the easiest homework problems you do in this class, right? I mean, it's not bad. But here I'm asking something slightly different, because this begs the question that of the integers, there's only even and odd, right? There's nothing else there. That's the kind of tricky thing in here. So you take any integer, it's either even or it's odd. How would I not know there's like a third category out there? How do you prove that? All right. So there's sort of two natural ways in my estimation. The one is to basically use division, right? But we don't really talk about division properly here till a little bit later. So the proof I want to give you at the moment is it kind of rests on an informal induction argument. We won't cover induction properly until after test 1 either. So, but I want us to have this result, and I want us to understand what's involved in proving it. So I'm going to do this today. But before we get to this, actually, we need a little lemma, which is that x in the integers, then x times x plus 1 is what? Oh, goodness. I'm like, I think maybe I need what I'm trying to prove to do this one too. Oh no. Sorry, my other proof just fell apart. You see, you look at stuff, people have proofs of these sort of things online, and you look at them and they seem like they're okay, but then I realize, oh, it's resting on something that the proof of which rests on exactly the thing I'm trying to prove, which then makes the argument circular. Like, I can't do that. So, all right, I'm stuck with division. I'll have to show you that. All right, so here's the proof. And admittedly, this is putting the cart before horse a little bit, but I have no choice. Let x be an integer, right? Think about this. Either 2 divides x, or 2 does not divide x, right? So, number 1, if 2 divides x, then x is equal to 2m for some m and z, which is to say what? X is what? Even, right? That's the definition of even. What's the other option? Option 2. If 2 does not divide x, this is the symbol for does not divide. We have the straight line with a cross through it. This is the symbol for does not divide. If 2 does not divide x, then division by 2 leaves a remainder, which is to say, if I was to take x divided by 2, right, I could write it as some number m plus, what does the remainder have to be? So the remainder has to be smaller in magnitude than the thing we're dividing by. That's the way remainder works for division, right? And we can assume that the remainder is positive. So now that's the part, so this right here is the part I'm getting before the cart before the horse. We haven't proved that division is a thing yet, you know. We will talk about this more systematically a little bit later in the course. But for now, you guys remember arithmetic from grade school. We can do division, right? So if that's the case, then what? X is what? Equal to twice times m plus 1/2, also known as 2m plus 1. Thus, you know, this is for x, for m, an integer, okay? Thus, x is odd. But that's it. Either 2 divides x or 2 does not divide x. Therefore, as you see, either x is even or x is odd. Right? I think all proofs of this either rest on the division algorithm, which we just used, or induction. But the division algorithm actually also rests on induction. Induction is a proof that involves natural numbers that's done carefully, all right? That's after test 1. Okay, so that's that. Now, once you know that, then you can go prove my lemma. Let me show you why the lemma was out of order. So like example 3 here, given x in the integers, right, then x times x plus 1 is even. How would you prove that? Once you know that integers are either even or odd, it opens up a whole plethora of new results. All right, like there's all kinds of things you can prove once you know that. So I'm trying to make sure I've got all my toys. Yeah. Okay, so here's the way that works. Let x be an integer, then x is either even or odd, right? So number 1, if x even, then x is equal to 2m for some m in the integers, right? Thus, x times x plus 1 is equal to what? Yeah, 2m times 2m plus 1, right? Which I would emphasize is twice j, where j equals to what? J is equal to m times 2m plus 1, right? Which is a what? That is a integer. So the product of x times x plus 1 is equal to 2 times an integer. Therefore, x times x plus 1 is even. Case number 1. What's case number 2?
X is odd.
Yeah, if x is odd, then x is equal to 2m plus 1 for some m in the integers. So then what? Thus, I'll be boring and use the same language. Thus, x times x plus 1 is equal to 2m plus 1 times 2m plus 1 plus 1, right? Which is equal to 2m plus 1 times 2m plus 2. We can factor the 2 out, right? 2 times 2m plus 1 times m plus 1. And k, if you like, equals to 2m plus 1 times m plus 1 is an integer. Thus, x times x plus 1 is equal to twice k. Therefore, x times x plus 1 is even. And we're done. I announced at the start that we're doing a proof by cases, right? So if I don't announce at the start I'm doing a proof by cases, I'm pretty much obliged at the end of the proof to say, okay, therefore we've covered all cases, and the conclusion follows, right? But if I kind of announce we're doing, if I announce we're doing a proof by cases at the start of the proof, then, you know, I think it's not unreasonable to not say that again at the end of the proof. Of course, you could also say it again at the end of the proof, right? If you wanted to be more verbose and lose less of your readers, or annoy more of your readers, depending on your audience, right? So, brevity is the soul of wit. I'm not that smart, so. Any questions? What do you guys think? So once we know every integer is either even or odd, all kinds of proofs we can do like this. Let me show you another one of these kind of things. That's maybe a little bit different flavor. I'll do it over here, I guess. So here's another one. What example am I on? Example 4? All right. Example 4. So all the proofs today so far have all been what? They've been direct proofs, haven't they? Essentially direct proofs. I mean, we had a direct proof that had cases in it, but essentially they've been, we have an implication we're trying to prove. We assume the antecedent, right? And then we show that the consequent follows. Sometimes the conclusion required breaking into cases, but, you know, I guess, did we break the conclusion into cases here, or did we break the antecedent into cases? I suppose we broke the antecedent into cases here, didn't we? Right? So this is a proof type. If we have a antecedent which has, you know, we can divide there's different cases in the initial hypothesis, then we can break into cases. If we can prove each case establishes the conclusion, then it follows that all cases establish the conclusion. I could write these things down more formally, but I'll save that for another day. So here's example 4. Let x be an integer. Let x be an odd integer, all right? Then either x is equal to 4k plus 1, or x is equal to 4k plus 3 for some integer k. So how do you think we should prove that? I had another proof ready for today. Where'd it go? Oh, there it is. I found it. Okay. So how's this going to go? So proof. We start with let x be an odd integer. So that is x is equal to, let's say, 2m plus 1 for some integer m, right? Now what? Then, either m is even or m is odd. Thus, consider, number one, if m is equal to 2k, then x is equal to 2 times 2k plus 1, which is equal to 4k plus 1. All right. Case number one. Case number two. If m is equal to 2k plus 1, then x is equal to twice 2k plus 1, which is equal to what? 4k plus 3. And we're done. Because we've just shown that if you have an odd integer, it's either equal to 4k plus 1 or 4k plus 3 for some integer k. I guess to be fussy, I should show that these cases are disjoint, shouldn't I? Because I've used this either or language, right? How do I know? I mean, this is kind of dumb. Is it possible? So let's complete the. I guess technically speaking, I am missing something here, aren't I? It's so obvious. It's almost, I would sometimes forget it. But notice, if x was equal to 4k plus 1, and it was equal to 4j, I shouldn't assume that it's the same integer in both cases, right? Like suppose there was a k that it was 4k plus 1. There was a j that it was 4j plus 3, right? For some k and j. Then what? What would that tell us? That would tell me 4 times k minus j is equal to what? 3 minus 1, which is 2. But this is impossible, right? But so then, which is, what would this say? This would say thus, 4 divides 2. That's what that equation says. It says 4 divides 2. But what did we prove earlier today? What did we prove? Do you guys remember? If A divides B, then B is what? Greater than or equal to A? Do you remember that? So this would imply what? 2 is greater than or equal to 4 by the previous result? Can we have that? No. So this is absurd. Thus, cases 1 and 2 are distinct. In other words, what I'm saying is, let me just kind of back up for a second here. We'll work an easier contradiction proof here in just a second. But so I'm assuming this, right? I've assumed this. Let's say I've assumed P, and I've showed that that implies Q and not Q, right? The Q is, you know, 2 greater than or equal to 4. But of course we know that not q is true, right? Not q is 2 is in fact less than or equal to 4, right? That's a contradiction. I can't have both 2 greater than or equal to 4 and 2 less than or equal to 4, which of course is true. So that therefore means that my assumption P is false. This is proof by contradiction. Now I don't always formally think of it this way. Pretty much I assume something like this. I make logical arguments and I find my way to something which is absurd, at which point I say, oh, okay, if that's the case, it must be that my assumption was wrong. Right? If you make assumptions and you make logical sound arguments and you reach an absurdity, it means your assumptions are flawed. Or your reasoning's flawed. But we can't, we can't quantify that. Although we know it happens. Here, let's look at an easier contradiction proof. Let's leave divisibility behind us for a second here. Let's just go back to a simpler time and talk about graphs of equations. There are lots of good examples from graphs of equations, after all. So here is example 5. Prove graphs of y equals to x squared plus x plus 2 and y equals to x minus 2 do not intersect. So the proof is going to be by contradiction. All right. So how do we begin? Suppose the graphs of y equals x squared plus x plus 2 and y equals to x minus 2 intersect. And I need to give a name to the point of intersection, right? So I think I'm going to use x naught, y naught. Why not? I'm sorry, that was horrible. I regret nothing. Suppose they intersect at x naught, y naught. Then what? What does it mean to be in the graph? It means it solves the defining equation, right? So then we have two things. We have y naught is equal to x naught squared plus x naught plus 2, and y naught is equal to x naught minus 2. Right? Thus what?
X naught squared plus x naught plus 2 equals x naught minus 2.
Yeah, so thus y naught is equal to x naught squared plus x naught plus 2, but it's also equal to x naught minus 2. So since they're both equal to y naught, this is going to get me. Since they're both equal to y naught, oh, I forgot. Here, attendance. If you could add a date, if you could figure out the date of the original column here, that would be helpful, because we didn't write that down. But we can cipher that this date is from before today. That much we know. So I'll just have to piece the pieces together. Anyway, it's okay. If you can add a date to this one, though, that will make this less ambiguous going forward. So it's my own stupid fault for not adding a date last time I passed the sheet around, right? Okay, anyway. I'll stop being an idiot at some point. So here we go. So what does this tell us? What's this imply? Hence?
X naught squared plus x naught equals x naught.
So hence x naught squared is equal to minus 4. Right? The x naughts, they be canceling. And subtract 2 from both sides, right? Algebra. But x naught is an element of the reals. And x naught squared is therefore greater than or equal to 0. This is a fundamental property of the real numbers. Any real number squared is non-negative. The square of a real number is non-negative. Right? Thus, I'm going to give it a name. Star is a contradiction. So sometimes, rather than writing contradiction, I like to write like this. Like two arrows that go against each other. It's a contradiction. Therefore, consequently, we find the given graphs do not intersect. This is proof by contradiction. Now, does the square of a real number being non-negative have anything to do directly with the intersection of graphs? I don't think so, right? This is the nature of contradiction. It's like where the contradiction comes or arises doesn't necessarily have to have any direct logical connection to the problem statement that you're facing, right? So proof by contradiction is, I don't know, in some sense it's unsettling. There's a whole class of mathematicians that, seek to avoid it. I'll talk about this in the notes some. They're the intuitionist school. They want to construct everything in mathematics. So the intuitionists actually work towards finding proofs that don't use contradiction, So one of the chief among these folks is Brouwer, if I remember right. Got some quotes over here. It's on page 30. So Hilbert says this. Hilbert's a famous mathematician of the early 20th century. He says, taking the principle of the excluded middle from the mathematician would be the same, say, as prescribing the telescope to the astronomer or to the boxer the use of his fists. In other words, the excluded middle is really important. The excluded middle is what proof by contradiction rests on. See, in particular that Q or Q and not Q. Well, we have the excluded middle back on our formula sheet. I can find it. Did everybody get these sheets, by the way? I see there's a couple left over. I handed out these. Well, here we have axioms and definitions, the number sets and system. Anybody not have this paper? Maybe? No? Anybody else? No? All right. So, in any event, Brouwer also was one of the chief proponents of mathematical intuitionism. His full name, Lutzen Egbertus. That's an awesome middle name. Jan Brouwer. So at an early age, he proved the highly non-trivial topological fixed point theorem. And he had some interesting opinions. He said that the following. He said, the construction itself is an art, but the application to the world an evil parasite. So not a fan of applied mathematics, all right? Not a fan. And anyway, so there are these different schools of thought, right? Should you use contradiction? Should you not use contradiction? There are just some things that we have to use contradiction for. Otherwise, you just can't see it through. But I generally try to avoid use proof by contradiction as much as I can. And it's not always possible. So sometimes you just have to. But one of my pet peeves is students who use contradiction needlessly. So I'm going to make it a penalizable offense in linear algebra next year because of one student did it too much last year. But anyway, I don't know if that's fair. And they are logical arguments. I just don't like them. All right. Here's another example. Example 6. But proof by contradiction rests on the law of the excluded middle. So you can look back at the sheet I gave you last time for that. So this is another example. Prove if m squared is odd, then m is odd. All right, and so I forgot to tell you what m is. So preamble here, let m be an integer, okay? And so far today we've just done proofs, direct proofs, right? We did a proof by contradiction. So now I want to show you what's called proof by contraposition, right? Listen to me, contrapositive. What's wrong with me? That's why I need to teach this class. So this is P, this is Q, all right? So if we can show, remember the tautology, we had what? Tautology, if I can spell, tautology, P implies Q. We can trade that for what? Not Q implies not P. And so if we want to find a proof of this assertion by contraposition. Contrapositive. What's wrong with me? So here's the proof. And so usually I say by contrapositive to warn my reader that I'm doing it. If I'm reading a book and they're using this and I don't realize they're using this, it confuses the bajunior out of me, right? Eventually I come to him like, oh, wait a minute, this is logical. But it takes me a second because I'm looking for the direct proof and they're giving me this thing here. So we'll suppose m is not odd. So suppose m is an integer and m is not odd, right? Then m is equal to 2k for some k in the integers, since m is even, right? If it's not odd, it's even. We established that today. All right, you can use that, either even or odd. So then what? Consider m squared is equal to, what we got? 2k squared, which is equal to
4k squared.
right? Which is also equal to twice 2k squared, where 2k squared is a what?
An integer.
An integer. Hence, m squared is even, so m squared is not odd. So we've assumed m is not odd. We've now proved that m squared is not odd. Therefore, by proof by contraposition, thus using proof by contrapositive, or if you like, contrapositive, we find m squared odd implies m is odd. End of proof. All right. Let's see here. Any questions? All right. So let's look at, this is a kind of bigger deal. If I can find it. I want to state it carefully. So here's a definition. So definitions are important. That's why I'm making the quizzes focus so much on definitions. You know, memorizing definitions carefully is a large component of success in this course. And it's also a large component of success in any higher level math course. Like definitions, you must understand precisely and carefully. As a best practice going forward in future math classes, you don't want to just know the definition like memorized. You also want to have an understanding of it, have examples, have counterexamples, things like that. But, you know, got to start somewhere. So definition, here it is. Let P be a natural number with P not equal to 1. Then we say P is prime if and only if the only factors of P are P and 1. All right, I don't think I ever defined factor in here, so that's kind of a problem, isn't it? I think I've defined factor in the notes, but I don't think I defined it in class, you know? So let me restate this in terms of divisibility. So what is this last sentence? Only, how can you guys tell me how I would restate this? Only factors of P are P and 1 in terms of divisibility? That means that
Divisible by P.
yeah, if, let's say, if x divides P, then x is equal to P, or x is equal to 1. So another way to say that is it's only divided by itself and 1. What does it mean to say that you have a factor, by the way? Like, we can define that while we're at it. If I say x, an element of z, has factor, let's say y, then there exists z in z such that what? X is equal to yz, right? That's the definition of factor. It's kind of another way of getting at divisibility, right? And factor is also related to multiple, right? To say x, to say y is a factor of x is also to say that x is a multiple of y. So we have these, you know, related family of ideas. Anyway, let me get back to the the prime business here. So it's a prime if and only if the only factors of P are P and 1. Furthermore, if n is a natural number and n is equal to AB, where 1 is not equal to A or B, all right, in the natural numbers, then n is a composite. So we're defining composite here, guys. Composite integer. If you like, you could say it's a composite positive integer to emphasize the context here. All right. You could also define primes for, you know, integers that aren't necessarily positive, right? Like I've defined prime for natural numbers just to keep the discussion kind of limited. And also because in elementary school, we pretty much keep it limited to positive numbers. If you were to extend the discussion of primes to all of the integers, it brings in new wrinkles, right? Think of it for a second. Let me just leap outside the realm of natural numbers for just a second here. What are the divisors of 5 if we think of it as an integer? 1, 5, what else?
-1,
-1, -5, right? So all of a sudden you got to address those issues. Every time you're proving something about primes, you've got the plus minus issue that you're facing, right? So to avoid that sort of duplication of discussion, we just focus on natural numbers basically. But there is a natural and obvious extension of this to the whole totality of integers. It's just the definition of prime, if you think in that context, is a little bit more broad. But typically people, when talking about primes, they're talking about prime in the context of natural numbers. So we'll do that as well. All right. So what does the fundamental theorem of arithmetic say? Do you guys know? So here's what the fundamental theorem of arithmetic says this. Fundamental theorem of arithmetic, or FTA. All right. It says if we take any positive integer, right, let n be a positive integer, all right, then there exist distinct primes p1, p2, ps, all right, and exponents m1, m2, m sub s for some s in the integers with s greater than or equal to 0. So, you know, I'm allowing the case of 0 exponents, right? Such that n is equal to p1 to the m1, p to the m2, ps to the ms. Notice that here s equals to 0. What is that? Why do we need s equal to 0 in this discussion? I didn't say what the I should say these. Well, I guess these. I'm sorry. My bad. These. I should. Oh man! What in the world? Seriously? New Jersey. That's a spam call. Let's see here. My apologies. But at least when your phone goes off, you know, I'm good company. So these are in the natural numbers, I believe. Okay. So the exponents are 1 or larger, okay? But notice that in the context s equals to 0, that gets us what? So s equals to 0 gives n equals to 1 in this notation, okay? Just to be clear, n equals to 1 is covered by the s equal to 0 case. So what's the rest of the theorem? If, you know, Q1, Q2, QR is any other collection of distinct primes, all right, and with and there exist exponents n, n1, n2, n sub r in the natural numbers with r in z such that r is greater than or equal to 0. All right. And can you guys see it if I write down here? If you guys don't mind, I'm going to erase the definition of prime and write the conclusion of the theorem up top where everybody can see nice and clear. So poor planning on my part. I should have chosen a smaller font up here. But I think you guys all know the definition of prime, probably before you started this class in all likelihood. Notice by definition, 1 is not prime. All right, so, and here we go. N is equal to, Q1 to the N1, Q2 to the N2, QR to the NR, then what? So what I'm saying is we have two different prime factorizations of the number n. One with the p's, one with the q's. These are distinct lists of primes. What do we get to say about R and S? How are they related? What's the punchline here? That was supposed to be a then. R is equal to S, and if we would look at these lists, Q1, Q2, QR, as a list, it's equal to, we could use a set, right? The set, this set, and this set, they are the same set. So if we find the prime factorization of an integer, it's unique up to reordering of the primes. You guys with me? Let's make an observation here in the interest of supporting our last example for today, which is an important example. So what we need here is, lemma. The lemma is actually going to just be the calculation here. N squared, what's it going to be equal to? I'll use the p's. P1 to the M1, P2 to the M2, PS to the MS. What happens when we square that? We get what? We get P1 to the 2M1, P2 to the 2M2, PS to the 2MS. Right? Let me put this into words. If n is this if n is equal to m squared for some m in the let me not use n here. Let's say x. If x is equal to m squared for some, I'll use n just to be less weird. If x is equal to n squared for some n in the natural number, then all the exponents in the prime factorization of x are fill in the blank. Give you guys a chance to think about it. What can you say about the exponents of a square? They're double. What does that make them in terms of the language that we've been using today? They're even. Right. They're all even. All right, so let's remember that. So, our last example for today, I've lost track of my example numbers. You guys help me out. What am I on? 7? All right. The square root of 2 is not a rational number. So let me remind you, rational numbers have the following form. They've got the form p over q, such that p and q are integers, and q is not equal to 0, right? This is the set of rational numbers.